going to, who's basically
going to focus this.
while Roy Yates is focusing this, we will welcome Zhong Ye from RPI. So he's about to receive his PhD, or at least defend his PhD next month, right? In about 3 weeks. So, and he's going to tell us today about rate adaptive spread spectrum systems, OFDM, and its use in tactical networks. So I'm really interested in finding out what that is like, most of us here. Because at least out here, right, we've been talking about packet spread spectrum or packet CDMA, but we always end up working on power controls. So it seems like I'd really like to find out what do you say you've done in your abstract. Okay.
Trying to get this done in a 45 minutes time frame.
No.
Take your time. We have an hour. And if somebody has to leave, please feel free to.
Again, this work is done during my PhDs at RPI for the mostly for the Air Force Research Lab, and we're proposing here a rate adaptive schemes based on spread spectrum and OFDM, and use that to meet the requirement of a tactical packet radio network situation. This is the outline of my talk. I will start pointing out some of the challenge of a tactical packet radio network, mostly dominated by multipath and jamming. Then I will introduce the key concept here based on the spread spectrum concept and apply it to a OFDM framework. I assume some familiarity here with OFDM. Talking a little bit about equalization techniques that we use as auxiliary schemes to enhance the system performance in excess of the maximum processing gain of the system. And the key trade-off analysis that we're doing in a spread spectrum system is to try to understand the trade-off between coding gain and spreading gain, and trying to come up with adaptation schemes with minimum control overhead and can apply it very easy in a real-world situation. And time allowed, I'll apply that to a packet radio network using multiple access schemes like ALOHA, CSMA, and CDMA, and then end my talk. Most of the work done are driven by the requirement from a tactical network point of view, in terms that the networks, the base station as well as the mobile can be constantly on the move at a much higher vehicle speed than most of the commercial counterpart. We're talking about the Air Force application here. And severe and unpredictable terrain, all this kind of make the multipath situation a lot worse than you would normally see. And I don't have to say a lot more on the intentional jamming from the enemy that lead to a larger low probability of intersection and anti-jam margin requirement for the system. And on top of this, we still need to guarantee the delivery of the high priority control message.
Sean, that's something that's always confused me a little bit with the interception probability.
Okay.
Why does one really care about that if you got encryption? Does it matter complexity of the encryption and the decryption?
Depending on at which level you want to apply the encryption, and if you already get to the level that you're going to try to attempt to decrypt, that's already at a level that they feel uncomfortable at. You don't have to really understand the whole message before you can try to jam the transmitter. So a key requirement is that they want all the signal to be noise-light to begin with.
It's not a matter of decrypting, it's a matter of jamming, identification. And
right,
jamming.
right. Okay. So in summary, the channel that we are talking about is characterized by very severe multipath from all these issues here, as well as interference. And these are some of the conventional techniques that to deal with multipath mitigation. I'm sure a lot of you are very familiar. It all boils down to some form of diversity, either in the space domain, frequency domain, time domain, or polarization domain. And the concept here is trying to regenerate it in an independent fashion, different replica of the same signal. And hopefully you can somehow intelligently combine these independent signals. Hopefully not all of them are corrupted at the receiver. And they have the advantage as well as disadvantage. This requires multiple antenna to begin with, which may not be a very rugged design to begin with. And for this purpose, so we kind of concentrated on single channel approach. Frequency diversity is easier if you combine it with a wideband approach. In this case, we use OFDM, multi-carrier. I'll talk about it a bit, and we use those. Time diversity usually is in some form of coding. We also deal with that. And polarization diversity is limited because you have a total of 2 to exploiting them. On top of this, these are other traditional schemes using adaptive equalization, spectrum, and multi-carrier modulation. And a driven force here is that we try to pick the best modulation schemes that has all this advantage, and yet at the same time will allow us to support multiple data rate at a very large variety of changing channel conditions. And the key idea here is the rate adaptive transmission. Basically, it boils down to you have a bunch of fallback modes depending on what kind of channel condition you are at. And it could be, in a very easy way to understand, a way of adaptive modulation, as I will show very shortly, adaptive coding system, combination of all these. Or we have our solution, which look at it slightly differently. Little bit about the intentional interference, which in this case is very real, and it can take many forms, like narrowband type of tone jamming, or in some type of pulse jamming, or maybe combination of chirping and all other various kinds of form. And the modulation that we propose needs to be adaptive in the sense that it can learn all this type of environment and try to survive. So traditionally, the current generation of the packet radio network has to deal with all this channel impairment from jamming and fading. And to guarantee the delivery of the control message, a user way has to be designed is to do the worst case scenario design. What's the worst case you can be, say, at a cell, at the boundary cell, or what could the worst jamming you have to guarantee the delivery of the message. And the result of this is usually a poor utilization of the channel resource, especially when the channel goes to a better favorable condition. So naturally, everyone will tell you that a better way is to adapt the transmission parameter in terms of constellation size, processing gain, transmission power, and variation combination of this. And hopefully when the channel is good, you use a better, higher rate, and when it's worse, you go to a fallback mode. And I don't need to say much about this here, assuming that all of you have the info station concept. So basically, this is a variable constellation illustration of a centralized base station and its cell size structure. Conventional design basically has to use some kind of a fixed type of modulation scheme, independent of where the mobile is located. And to better take advantage of the varying degree of channel condition, you can say, if the channel is near the base station, you can use a very high constellation. And when you move toward the edge, or even beyond the traditional coverage zone, and you still want to maintain the control message, then you can fall back to some very low rate type of modulation schemes.
So this is a constraints there. I'm sorry to be nudge, but what are the constraints there? If we say you should be close, you should do this. You're assuming an implicit power constraint, transmission power constraint from the mobile.
Could you speak louder?
Yeah, is there an implicit power constraint from the mobile that you're assuming here?
Basically, this is just an illustration of saying that let's say the path loss dominant the receive signal stream. So the closer the mobile to the base station, in general, the channel condition in average will be better than a user sitting at the boundary. And you're trying to exploiting depth.
Yeah, assuming some limit or boundary bound on
Right.
how loud a user can yell,
Yes.
essentially.
Right.
Not multiple. Not everybody is everybody using the system at the same time?
They can share on a TDMA system, or they can individually switch the channel as a contentional free CSMA or ALOHA. It doesn't matter.
Each user there is assumed to be on its own channel, independent of the other users. You're not.
I will talk about the impact on multiple SS scheme like ALOHA, CSMA, and CDMA system at the end. So it doesn't matter. The user can simultaneously switch the channel, or they can share the channel on a time basis or frequency basis. And I don't get exactly what the question is.
I'm looking at this, and when I think of an InfoStations model, I think of I'm trying to optimize my capacity into the fixed network, so I should only transmit when I'm within a certain range. I certainly understand that, let's say the users in the red, which are the closest ones that I can really see and identify with my bad eyes.
Okay.
So they're transmitting.
There's a trade-off from a network throughput point of view on how far extent you want to support. There's a cost there. The farther away the user needs to guarantee the delivery, the drag down on the total system throughput that we'll introduce. And there's a limit that how far you want to support this. You cut the line there. But the bottom line here is that this picture is illustrated. There should be some type of adaptation on the rate depending on the channel condition.
I'm just trying to figure out what happens at that receiver. What you're essentially saying to me, and correct me if I'm wrong, is that the SIR for those red users is much higher than the SIR for the users at the periphery.
I don't think there are any users here, Chris.
What
It's
are
just saying,
those dots?
no, it's just like what modulation you use based on path loss from the base station. So you're right, it's just a fixed transmitter power. So the farther I go, the lower receive power I have, so I just use it. That's it, that's it. That's all it is. So I don't think he's implying that there are several users. He's just saying you have a constraint on transmit power. Just a single user. Constraint on transmit power, and let's say I just look at path loss as my primary thing.
Which is my receive power. The
Right.
capacity goes down, yeah.
That's all. So he's saying, so
For
you left
fixed power at the
fixed
user.
transmit. Yeah.
Is that
Is that the situation?
It could be a single user. I talk about it could be a multi-user situation like
That's what
CDMA.
So I think if you say multi-user, right, I think he's having a question.
My only question, it's a very simple question. This is nothing, this is not rocket science. Because you know this much better than I will ever know it. What I want to know is that for those red users, is there an implied, and the brown ones at the periphery, the oval-shaped brown guys at the periphery? In your model, it seems I would have to assume that at the base, they receive with different signal energies.
Yes, but if you throw in the considering the factor of the different modulation scheme that they use, assuming that they transmit at the same power level.
Yep.
Okay, the effective EB over N0 would be the same. That is the bottom line here to guarantee that they have the same performance. If you're looking at the base
Same
station.
performance? So what you're telling me is that if we have the same bands to play with, and I'm received, you're closer, we have the same band, I have to assume that there's some constraint, so you can only yell so loud.
You transmit at a much faster rate.
Oh, I increased my bit.
Given that there are various ways you can do this. You either use a higher constellation modulation, or you use less coding, less spreading.
If I attach a spectrum analyzer, I'm really sorry to tie you up. I'll stop in just a second. If I attach a spectrum analyzer to the signal of the brown guy and look at it, how wide is it?
They use the same bandwidth.
They use the same bandwidth. And
They use
have the
different
same-
redundancy. Okay, that's
You see where
They all use the same
Base
bandwidth,
rate is lower.
variable rates, so essentially the spreading factor is different for different users.
Go down to there when it gets the OFDM framework, it will become easier than this illustration picture.
P over N0W plus 1 log of the thing, W out front. You fix W, you're decreasing P. The rate goes down. So I guess I'm just trying to understand the constraint.
Shall I try to hold on to that question? I adjust that.
But mean power is getting down. If you introduce big distillation, mean power is getting down.
Yeah.
If you have 2 points,
Yeah.
you're achieving the smaller bits per hertz than when you have a 16 points. But effectively in a capacity relation, you're affecting power.
It's a very, I have Shannon's formula sitting in the back of my mind. If you're farther away, you receive less power using the same bandwidth, your capacity goes down, period.
Let's see if we can answer that when we go to a OFDM framework.
John, sorry to, be a bitch about that.
No problem. Not at all. Let's look at some of the characteristic of this conventional rate adaptive schemes. And I mentioned you can do it in terms of power or in terms of modulation and coding on combination of both. We take a different approach than most of this conventional system based on some of the disadvantage. And power control usually, to begin with, may conflict with the requirement of the LPI and LPD to begin with. And in order to handle deep fading, it could, on the other hand, create additional interference to the other user. And variable coding system usually support a narrower dynamic range constrained by the receiver's complexity. And it usually requires some fancy equalization approach when it goes to very high constellation point associated with the adaptive modulation. And what we found out, especially in a highly correlated channel, is that lowering of the coding rate does not necessarily value same amount of reward associated with the lowering of the coding rate. And you can improve the system with interleaving and all those, but usually at a cost, and I'll talk about those. And most of this adaptive modulation start at a condition that when the signal goes to beyond certain threshold, you bring this adaptation like the water filling approach. And when it drops down this threshold, usually it shuts down the transmission completely. And usually that is our starting point of the military application, that usually the SNI is pretty poor to begin with. And so we kind of look at the problem and trying to come up with a solution which is a combination of the OFDM and the spectrum. And you will see that it achieved a lot of the benefit that we proposed. Very briefly talking about the OFDM. Basically, it transmits the data in parallel, just like frequency division multiplexing schemes, and the carrier spacing is carefully chosen to maintain the orthogonality at the receiver. And typically, this is the spectrum that you are looking at. And the transmission and the receiving operation is typically associated with a FFT type of operation. As you can see, for illustration purpose here, Manning's narrowband carrier conveying individual message replace one wideband carrier. And the long duration of the symbol helps the system performance in a multipath type of environment. Any questions so far on this transmitter-receiver pair? Okay. So
are you going to talk about that, John? Adjust the constellation size on a per carrier basis?
That is actually, you can doing a adaptation based on the individual subcarrier level. And we're taking a slightly approach here by meshing this with spectrum. What we are proposing is that let's send all the information redundantly in order subcarrier. And the coherent combining at the receiver will deliver the processing gain as the direct sequence old-fashioned system. And the signature here introduced will allow the freedom for CDMA, but it's not a requirement. So we throw in a lot of frequency diversity here, and the amount of redundancy is basically the number of subcarrier in the system.
So your signature is on frequency?
Yeah. The frequency, you can think of everything in a frequency domain, and the transmitter basically converts this modulated in individual subcarrier into the time domain. and the receiver, the forward FFT will demodulate into the bin-by-bin operation.
Is it really, is it something different than a repetition coding?
That's a very good question. You can view it if there is no coding embodied on top of this. This can be viewed as a repetitional code in the frequency domain. And what we are studying as a trade-off is comparing this and some kind of coding and see what's the best way to allocate the system resource as we goes on. So what we are proposing here is, depending on how good the channel is, let's throw in as much as necessary as redundancy. In this case, we're throwing a processing gain of 2 in a total number of A subcarrier, and varying the amount of redundancy depending on the channel condition. So you can view it as a variable processing gain wideband system. This is just an illustration for A subcarrier. And in summary, what we are seeing here is 2 extremes. The conventional OFDM system with very high rate overlapping spectral efficiency and a very high protection for the full-blown spectrum system. And sitting in between is this variational Rate Adaptive OFDM system. And what we are proposing is, how do we track all these channel conditions dominated by multipath and jamming, and have a very uniform control strategy to control the processing gain.
So the rate adaptive is in the sense that you change your processing gain. That's how you sort of get it.
We change the processing gain and we throw in coding on top of that, but our conclusion is the coding rate can be fixed so that we have very little control knob for the whole system. And I'll justify that.
So when you say low tolerance to channel impairments, what do you mean? What are the impairments?
Multipath and jamming.
Jamming.
Okay.
Why is multipath an impairment?
What's that?
Why is multipath an impairment?
Multipath, because we're talking about base station, could be an airplane. Warrior can be on the ground moving. This huge Doppler type of characterization end up with a fret fading or selective fading type of environment. And if you don't do anything about it, as you will see, you have to throw in a lot of processing gain to get it out of the defect. And we justify that a better way to do this would be, say, let's segment the fading channel into, say, a Markov chain or something like that, and we carefully monitor the changing process and control. Instead of throwing a lot of processing gain, depending on which state, say, the channel is, we can have very little processing gain to get you out of the condition, and things along that line.
But how fast is Doppler you're talking about?
We're talking about, let's say it's much faster than driving at 55 miles an hour. Airplane can be moving.
But you need feedback to tell, okay, the channel is good.
I'll get to those implementation issues and as time goes on. Actually, one of our contribution is we're using this to LEO satellite application. The Doppler could be even higher at, say, 30 kilohertz to 60 kilohertz just for the Doppler offset. And we use this platform in those applications. I'll talk about the implementation issues. Just to go to answering Professor Menem's question. Say this is a fading type of Markov model. And by carefully matching the processing, there's a lot of details here that I'm skipping. But the point is, by carefully matching the processing gain of the system to the state of the channel, we can have an advantage in terms of the system throughput compared to a conventional fixed rate system. And we try to use this system from AWGN channel to flat fading to selective fading and try to maintain the same platforms.
So hold on, let's go back a second. So So that's the average SNR.
This is the average SNR of the channel, and conventional fixed rate system, as I mentioned at the very beginning, have no other choice but to take care of the worst case scenario if you want to guarantee the control message to get through.
Show us your channel again, I think is what we're using.
This is, say, a flat fading channel, have a number of states, and the transitional probability of those Markov chain is largely determined by how fast the time varying of the channel. And typically that can boil down to some type of Doppler frequency.
So what are you thinking? Are you thinking of an error as a bit error?
To just split that.
When you say probability of error given state I, you're thinking of that as a like this is a discrete
Let me say that
chain, right?
If the channel is very slow time varying, then it tends to stay at one state for a long amount of time before jumping to the next.
I understand. So you have associated with each state S1, S2, right? It's
Right,
some SIR, gamma, something.
Right, that's basically the received SNR as, and you kind of segmented that into.
So you're actually saying, oh, given your state I, there's some PDF f of gamma given I for the SIR in state I.
Let me put it this way. Let's say you have an average SNR for the channel.
Yeah.
And then it can be much higher or much lower for the whole lifespan of the channel. And so it will traverse along this Markov chain up and down for the whole fading process.
I just want to, excuse me. I just want to understand the how long do you think you're in one of those states compared to how long you think a bit is, say, to generate that next plot.
Okay. The duration that you stay in one state depending on the threshold. So how fine the resolution you want this adaptation to begin with, and it depending on the Doppler frequency. But you can calculate all this along a typical Rayleigh fading given a Doppler frequency and the threshold that you want.
But in your plot, right?
But in your plot, that you made some assumption.
Something. You have to assume something in your plot.
This is a Rayleigh fading. The assumption. I skip a lot of details here.
No, but in the plot, right, what was the rate of fading? What was the assumption of the rate of fading? That's what I think essentially the question is.
Yeah, more or less.
Is the fade the same over a bit? Is it the same over 2 bits? Is it the same over several
Okay,
bytes?
that's a very good question. What we are assuming here, we're starting with assuming we have a package structure that I skip, okay?
No, that is my other question.
And you
I'll
can
ask you after you answer this one.
And what we find out is the attribute of this scheme is that when the fading is very slow, we adapt to it. When it is too fast, associated with a lot of feedback and overheaded, it may not be justified trying to keep track of the up and down. Then we use additional diversity schemes that I will talk about to handle those. You don't adapt when it's too fast to keep track of. So there's a bottom line here, depending on how fast is fast. But beyond that line, you're trying to do adapt when it's slow. When it is too fast to adapt, you're trying to use coding, frequency diversity, and all those. You're trying to exploit those to handle the average channel condition and let the average channel condition dominate your performance because it's too fast to track.
So on somebody else, go ahead.
You've got just information about SIR. How do you link your SIR information with your frequency? Actually, you said that you could deal with frequency selective channels. How can you link your SIR with frequency and deal with frequency selective channels?
Let me go back. I think I skipped too many slides here. Okay. This is a reselective fading model. Basically, our approach is directly related to a rate operation at a time domain that you try to pick up the energy from the 8 individual rate. And what we are doing here is study the system performance at a spreading of 1 to 64. And you will see that the spreading give you system performance improvement until it reached the number of diversity available in the frequency selective fading. And this is dB over N0. Spreading further beyond that doesn't buy you any good. So essentially, this system that we propose by using spreading and frequency domain interleaving will deliver whatever amount of frequency diversity available in the channel, as if it is a rate receiver, but it's done it different in the frequency domain. And so that's the basic idea of rate adaptive OFDM.
Okay, so your rate adaptation is, you showed these things about adaptive modulation, right?
Mm-hmm.
A little mixed up. So you're just doing this adaptation for a fixed modulation, but you're just changing the spreading.
Right. And
So did you do something with the adaptive modulation, the initial picture you showed? Did you do something with that?
I mentioned about the difficulty on going to high constellation point using that the demand of fancy equalization and the compromise that with the LPI and LPD for a military type of operation, that kind of the dominant the adaptation of very simple modulation, but on a spread spectrum type of signaling format.
So essentially, you're saying that the low probability of intercept and whatever the other requirements of your channel of your system make it such that the best thing to do is just change the spreading.
Right.
Is that your point?
Yes. And the coding part, I will fill that blank in the following talk. And the other contribution that will come here is a adaptive equalization in the transform domain. And so very briefly touch on the equalization issues with OFDM. And as I mentioned in the beginning of the early talk, that traditionally this is done with some kind of cyclical prefix approach that take up some additional bandwidth. And what is
Another Mr. Boat sort of question. With the OFDM, what you're assuming then, I guess I'd let you gloss over that initially. You're assuming sinusoidal carriers
yes.
as opposed to the real channel eigenfunctions, which looks, if your aperture is wide enough, they look almost sinusoidal, but they're not quite.
Based on the FFT type of transmitter receiver, the sinusoidal is the assumption.
Right, so that's...
But it can be any type of orthogonal signal base, and we did have works on other lab transform type of signal base other than a sinusoid. But to answer your...
Yeah, I was just looking when you said it's compromised, but that would only happen... You're not calculating the eigenfunctions. You're using sinusoids. That's what you said. It's FFT-based.
And basically, the multipath here will introduce ISI, and on top of that, because of the multipath, there would be signal leakage from neighbor to neighbor, and causing the interchannel interference. And traditionally, this is handled by a cyclical prefix that can kill these two birds in one stone. But it needs additional bandwidth, and there is other penalty compared to coherent combining schemes. And so what we come up is some type of cyclical prefix-free approach and doing the adaptive equalization in the transform domain. Keep in mind that we are talking all this on a spread spectrum OFDM framework. And our goal is to handle the ISI and ICI without using cyclical prefix, and to be able to perform the rate operation in the frequency domain, as well as suppress narrowband interference all at once. And this is what we come up with. We have three equalizer structure, and this is the simplest one. We call it one-dimensional LMS operation. Essentially, we throw in a layer of forward taps to correct whatever channel impairment did to the signal, and using some kind of adaptive schemes to learn this channel. And this works well to knock down the narrowband jammer very well. And it does okay in an ISI type of environment, in which we come up with a solution to add a decision feedback stage on top of it. I'll show an illustration by how to use all the effective energy in the signal.
One last thing, this is a single channel, so this is not a scenario where you have a common base that everybody's talking to and they see different channels going to that base.
Absolutely right at this point. And in order to use all the useful energy, we throw in a second layer to collect the delay version of the signal. And these three equalizer schemes can be illustrated here by this diagram. What we are trying to accomplish is to do coherent combining, avoid ISI by the decision feedback stage, and collect all the useful energy that exists in the multipath channel.
Hold on. So, can you just illustrate to me what the new contribution here is? Because this seems like the standard decision feedback equalization, where you do feed forward and feedback.
What we're doing here is
so. Can you just explain what the novelty you said was?
Okay, we're doing it in a spectrum OFDM framework that everything is done at the frequency domain. All you're talking about is the time domain application, adaptive filtering, carry of narrowband jamming, carry of ISI. But all of these are done at the framework of OFDM and spectrum. We do all this without using cyclical prefix approach. We carry up the narrowband jammer, we carry up ISI at the same time. This is done at a very efficient way compared to the time domain implementation.
Okay, so you're saying that you're doing this in the frequency domain?
Yes.
That's the...
Can we see again the receiver, the TMA?
Oh, sure. This is the two-dimensional receiver that we have a multi-layer forward taps at the forward section and a decision feedback section to carry up the ISI.
So is this a time delay or what kind of delay when you say you're dealing with frequencies? What kind of delay is that?
The operation at this point is at the frequency domain. And the delay here that I'm putting in here is to gather whatever left over. Yeah, that's the time delay in the bit.
So it's some kind of multipath, some kind you're using diversity here. With that delay, why did you introduce that delay?
Okay, if you look at this carefully, the color basically, the blue one is the desired signal, okay? And the red one is the thing in the past, and the yellow one is the thing in the future. So you're trying to bring back something in the future while trying to remove anything that in the past that is doing bad things to you. So that's why you need the multi-layer or forward section as well as the feedback section to cancel the ISI. This is in terms of time, okay? So what we are proposing here is an adaptive transform domain equalizer that can take care of narrowband jamming as well as ISI at the same time. And we hope that this equalization will be compatible for the rate adaptive idea so that we don't have to retrain all those equalizers upon rate adaptation. And that's exactly what we get. So keep in mind, we're still doing the rate adaptive environment. And because of all those pathways of the adaptive equalizer is controlled only by the channel, when you change your rate, they are already converged to the correct pathways. You don't need to do any retraining. All is needed is just an intelligent way to coherently combine the right number of subcarrier using the already converged adaptive equalizer pathways. Any questions so far? So we talked about rate adaptive OFDM, we talked about equalization, and let me just go to coding. The ultimate goal here behind adaptive signaling is better utilization of the system resource. And we know both spreading and FEC coding will give the system better performance. At the additional cost of bandwidth. So naturally, we want to study, do you spend all your money in building a better, lower rate coder, or do you just controlling a processing game? And which one will give you better performance? That is exactly the motivation here. And we want to see if the coded system performance is coded dependent. So we studied convolutional coded system, we studied resolvent coded system, and concatenated coded system, trying to come up with a control strategy that will give us acceptable performance at a minimum adaptation cost.
So you are changing the bandwidth, and that's multi-circular, that bullseye structure that you had. You
No,
are
the
changing.
total bandwidth is fixed. Keep that in mind.
But each user can use some of the bandwidth or
If
all of
it
it.
is a single user, then it is the redundancy you throw in either spreading or coding that is variable. But the total amount of RF bandwidth is fixed.
Okay, so
Of course, you can dedicate a portion of that to one user and doing that on
Shannon isn't coming into it, is the point.
Okay. And let me see. I'll just go very quickly to the conclusion we reached. If you want to go to the detail on this.
No, let's see the conclusions first.
Okay.
So essentially, you're just talking about a coding spreading trade-off, and you're trying to do it in the presence of what you call as rate adaptation.
Yes, exactly.
Right? So here's why I'm getting all mixed up, right? Because your rate adaptation, essentially, as you call it, is just nothing but changing spreading.
But if
Right.
coding will do you better results than controlling the spreading, then that is not true. What we want to justify is that spending the same bandwidth expansion for coding will not do as good as given a fixed rate coder and varying the redundancy to only spreading. Let me see if this makes sense. Let's say you have a degree of freedom of A for the bandwidth spreading. Do you do a quarter for coder and spreading for only 2, or do you do a 1/2 rate coder and spreading for 4, or do you do no spreading but using a very low 1/8 coder?
Right? No. I'm very familiar with coding spreading trade-offs for a fixed bandwidth expansion.
Mhm.
Right. My question is, what is it that is different here that makes this? Because other people have looked at it, I guess, several times over different.
Okay. The
So what is the
conclusion-
difference here?
Conclusion is, so far nobody have this conclusion, is that
Okay.
it's justified we use a fixed, approximately 1/2 coder, and dedicated the rest of the resource to bandwidth spreading.
So isn't that sort of roughly the conclusion, though, of both the Kirby and Clee?
No.
Rate 1/2, rate 1/3, new code. And
Well-
what's the difference?
What are amongst the traditional academic is that a very low rate coder will always do better.
Right. But it depends on the channel. So what's the assumption of the channel here? That's what I want.
That's the good point. We are dealing with a large broad range ranging from AWGN to flat fading to selective
Okay.
fading.
See, he's just talking about across his class of channel models, right? His conclusion, he finds that this seems like whatever the optimum one. But for an AWGN, it's basically the lowest code rate is basically the best.
And what this result is optimum for resolvent and concatenated coded system.
So
for convolutional coded,
what's the definition of optimum?
What do you mean by optimum?
optimum means that it's counterintuitive of using a very high coding rate for convolutional coded. This is not the best system you will get if you don't worry about adaptational cost. For resolvent and for concatenated coded system, not only does the 1/2 rate coder does the best in terms of VER versus EB over N0, but it also giving you the best adaptation strategy. And
in what sense? Like based on...
let me show you in terms
comparison
of,
to-
okay, let me show you what I have here. Okay, this is what I'm talking about. For resolvent coded system, say this is an AWGN channel, the rate 1/2 coder, about A over 15, associated with additional spreading of A, is this system here. And we are looking at VER versus EB over N0 here. and the rest of the other combination doesn't come as close. And we look at the same trade-off study.
Hold on, don't go away so fast.
We have a fixed bandwidth spreading of about 16 here.
Sure.
And we're looking at what's the best system giving you in terms of BER.
So your best system there is 8/15.
And spreading the rest for processing.
Yeah. Okay. What is the assumption on this channel?
This is an AWGN channel.
Why isn't, if I go to, what is it, let's say, what makes it 1/3? 3/15? No, 5/15?
That's,
Why isn't 5/15 better than this?
and I will show you with a analytical justification of this. But bear with me, we see the same trend for a full-rate selective fading.
No, let's not go to fading. I just want to understand it for AWGN, right?
Okay.
AWGN, my understanding of the interpretation of Joe Huey and Viterbi and all these people's results is that... if
Those
you
are
have-
convolutional coding. Keep in mind, this is for
this is for read solvent.
Yeah. This is the asymptotic coding gain that we come up with, trying to see when the SNR basically goes to infinity, what's the coding gain you will get. And we throw in, for hard decision decoding, we throw in the number, the coder that we use, and the error correcting capability using hard decision decoding for resolvent code. We are seeing here the best system is actually the one with about 1/2 code. And the same trend is true for a soft decision decoding for the resolvent code. So bottom line is that we justify this for a resolvent code, which is very popular block code in this type of block operation. For convolutional code, what I'm saying is that the same strategy may not be the optimum in the sense that we don't see the same clear-cut advantage of the 1/2 rate coder, but we justify that if you throw in the adaptational cost with it, the gain with additional lower of the coding rate does not buy you any good as compared to what we propose.
So you compare the BER, not the throughput.
It will go to a throughput by a...
No, but here you just say, okay, I gave you the code rate.
Let's say
BER is better.
if the BER is not as good, how can you do better in the throughput?
No. Your throughput is just is include your BER.
You can have a one-to-one relationship between the BER and the total system throughput, and we have studied on that too.
No, because the question comes, you say, okay, if SNR goes infinity, what's the coding gain? But if your SNR goes infinity, no coding is the best. Right? So
No.
you don't need coding to your SNR infinity.
No,
That's to get the best throughput. Why do you need coding for it? SNR goes infinity.
no. The asymptotic coding gain is just that you compare what's the best you can get. And we try to justify this in seeing a counterintuitive type of phenomenon as what he proposed, like by Antogodrubi and all those people in convolutional code. We need to understand why it's behaving like that.
Yeah, but the question, okay, is that when you compare this different coding scheme, right? Is you just compare the BER or you compare the throughput? Because you want to achieve the best results for your system, that you're talking about the throughput.
At this point, it's still physical layer stuff, okay? I will talk about
Right,
link
so
layer.
no, I think he has a valid question. He's asking, like, why should I believe this is the best for the throughput?
No, I didn't say it's the best for the throughput at this point. I'm saying it's the best from a physical layer parameters point of view.
No, from a bit array optimization point of view, you're saying that the half-rate code seems like the best thing to do.
Yes.
Okay.
I'll definitely go to the network layer, and that's part of the contribution that we do.
And hold on. When you put a thing like that, right, you're telling me this is good no matter what the rate of fading is?
We try, of course, different...
I mean, look, I refuse to buy that, okay? You just can't say that this rate half will be the best no matter what the rate of fading is. So what's the rate of fading here for these curves?
Okay, I'm talking about a fast fading. In terms of fast, I mean that interleaving is able to throw in the independence of the code words.
That's right,
This
okay.
kind of thing. Okay? There are a lot of details here. This can go 2-3 hours easily, but I try to make.
Okay, so from that point of view, essentially, this is just like your independent errors.
Mhm.
This is as good as the error assumption on the AWG channel,
Right.
if you will.
Yeah.
So that's why you still see the same results.
And it's so far we go through. This is the approach we take. We look at interference suppression for multipath and for jamming, and we come up with the rate adaptive idea that can adjust the processing gain in terms of the channel condition. And now we want to see the networking impact of the schemes.
Okay. Before you go on to that, right, just one quick question. So you said you're going to tell about how you implement this. So how do you implement the rate modulation, adaptive what do you call it, whatever, rate adaptive scheme based on channel conditions? How do you do that?
Okay, good. Let me
Okay,
go
let's-
to that directly,
let's-
okay?
Okay.
The key to make all this works is to have a good channel estimator that is able to precisely determine what state the channel is, and then there are two ways to do this. You do a direct measurement-based closed-loop approach, or you're doing some type of inference-based open-loop approach. And these are the link assessment that you need to do for a closed-loop approach. Typically, at the receiver, you do the measurement of this parameter, and somehow feedback is needed from the receiver back to the transmitter in order to control that. And
So then it seems like just based on the kinds of things you're trying to estimate, right? Then an adaptation has to be quite slow. So you cannot really say it's like. Yeah, exactly.
Hold on. Let me show you if I can find this thing, the package structure. Bear with me with a second.
Are you now analyzing the same receiver that you gave a picture with all the NP equalizer with, I'm a bit confused. All these blocks are still in the receiver?
Okay, this is a package structure.
I've got a question. You gave us a picture receiver with those little delays, with the decision feedback
Those
equalizer.
adaptive equalizer.
Are you still the same system you're evaluating now?
At the receiver.
Totally nothing excluded. This is you're analyzing the system completely as it is.
So this is a package structure that we propose that have like a unique word for equalization training, for the rate indicator and associated FEC with it, and all these are transmitted at the maximum processing gain, while the payload of the packet is done with variable processing gain, whatever needed by the channel. So go back to that implementation issues.
Sorry, could you show that packet again? Packet breakdown. Flip it over.
Flip it over.
There you go. Yeah.
So 2% forward error correction on what? On the
This is the only thing unique of this versus a fixed rate system is the rate indicator. And whatever
what's the
error.
FEC? What is the FEC?
FEC is just to guarantee that the rate indicator is reliably detected at the demodulator so that it can demask the following data associated with it. It's optional.
So the FEC is applied to the thing that comes the header set.
Only the rate
Only
indicator.
rate indicator.
Yeah.
Okay. Let's say, show me that code. Apply to the data.
So I'm assuming a lot of you are familiar with the networking issues, but what we are looking at just now is that how to implement this. And a unique way to see this is that if we cannot do the channel estimation very robustness, there's no point of doing all this rate adaptation. And what we come up with mostly the contribution is some inference-based link adaptation format that allow us at the receiver, you will, instead of doing the direct measurement and feedback and all those closed loop approach, we're trying to predict what the next day will be, basically. and use that to our advantage. And we find very successful application of this approach in a LEO system. If you like, I can get into that. And over here, no feedback is needed from the receiver to the transmitter. And what we are doing is trying to infer the channel condition based on what you observe. And the implementation, depending on the duplex schemes and the tolerance of Doppler and bandwidth and all those that you were able to handle. And eventually, we kind of combine the open loop solution with a infrequent calibration of the closed loop to make it very robust against rate attenuation and jamming, etc. So if that's what you guys want, let me get into the LEO system very quickly.
So what were those implementations for? I'm sorry.
Those are trying to answer your question.
Okay, good. All right, so it's
On
basically
how to
how you do the
channel, yeah. Motivation here is that very high flight speed and the low altitude of the LEO satellite system. And worst case scenario, again, lead to bad channel utilization. And we have all those requirements from LPI and AJ. I don't want to say more. And let's look at the channel. This is basically determined by three factors: free space propagation, multipath fading, and other type of factors.
Where are the antennas usually? I don't know. For the LEO satellite stuff, is it an oblique projection, or do you point your dish pretty much straight up?
At the satellite, this will usually be a down loop antenna. You know, when you're talking about a satellite.
I understand. It talks to a base station, right?
Yeah, the base station right now is the one that is flying. So what we are looking at here is a simple sketch of the Earth and the satellite orbital plane. And basically, a LEO, if this is the mobile user on the Earth, you will see the satellite approach at the horizon, go over your overhead, and then moving away from you. So there's a large degree of freedom here in terms of receive signal strengths observed by the mobile. What we are trying to do is precisely predict this trajectory based on the measurement of Doppler frequency. I'll talk very briefly. That measure at the mobile, and use those to our advantage to finish the control of transmission parameter.
And once again, there's a footprint associated with that, or is there? Is it an omnidirectional satellite? Is a footprint? Is it oblique? I'm trying to get an idea of what sort of Doppler effects I could expect. If I'm looking straight up, I would expect the same amount of Doppler.
This is the
over
Doppler.
the
This is the Doppler versus time that you will see.
So it's fast, just where? It's fastest at the edges.
Right. Okay. This is the Doppler versus time that you will see. The LEO satellite Doppler frequency observed at the mobile here exhibit a well-behaved S-curve, so-called S-curves, versus time that can be characterized by one parameter, the maximum elevation angle.
Now, once I'm going to ask again with this LEO, I don't know the exact numbers, but I'm assuming that this LEO is not an omnidirectional antenna. It's a phased array sort of thing that points in a particular direction. Is it being steered as it goes, or is there a footprint passing over the base?
There's no fancy control like the footprint that you just mentioned. And what we are trying to exploit is, under such situation, what's the dynamic range of the resisting strength that we can exploit.
So you're assuming essentially an omnidirectional bird.
Yeah. Okay. So over here, the satellite show up at the horizon, moving quickly over the head, and then departure away, and is characterized by the maximum elevation angle observed at the mobile. And turn out there's a one-to-one relationship between the Doppler and the instantaneous elevation angle. There's a closed form here. Again, characterized by the maximum elevation angle. And do a little bit geometry, you can translate this into received signal strength observed at the mobile.
So that's horizon to horizon in about 20 minutes.
Yeah. In this case, it's a global star. I'll put down the constellation in a few slides. So you will see about 11 dB in terms of the just the path loss. And the second factor that we want to consider is the fading. So we put in a typical non-geostationary time domain fading simulation that trying to understand the long-term behavior of the fading, because the short-term up and down is too fast to track.
Excuse me. This channel is sort of like rising channel, right? You always have this line of sight. Right?
Just the direct line of sight
So
component.
it's like I was wondering what the K factor or the rising factor for this.
This model is more on a statistical measurement on the trial data and fit it to these three parameters that controlling the line of sight component as well as the non-line of sight rayleigh fading part of it. And all these three parameters are direct measurement of the global star system and tie them to a very close relationship to the elevation angle.
So how's the line of sight component compared to the scattering component? So like 10 dB or 20 dB?
If you translate it into that K factor thing,
Yeah. I was
and
wondering.
it depends a lot on this elevation angle again.
Okay.
So you will see that there's about 7 dB here on the average fading magnitude that you will observe when the bird passes from the horizon back to the horizon. And this is the range that we want to exploit. So we have to understand how wide this single dynamic range is to begin with. So what we are seeing basically is that the fading is high at the low elevation angle and high at the overhead. And it justifies the need to speed up in the middle of the visibility window.
The pulsations writ large.
So the bottom line is that if we put all this together, we have about 27 dB from path loss, from fading, from antenna angle, and from the ionospheric loss, and which allow us about one spreading factor of 1 to 500. And to get to this is basically what we're seeing here for the global star. And we are proposing an algorithm to use 2 Doppler frequency to precisely predict those family S curves that we see, and use that to our advantage to precisely pick the processing in when the satellite is passing in the visibility window. So I'm trying to stop here for this LEO application, and going back to kind of wrap up what we've done. So we look at interference and multipath, and we look at adaptive rate modulation. The last thing that I didn't talk about is the networking issues in terms of system throughput. What's the best system given this rate adaptive engine? We talk about ALOHA, talk about CSMA, and talk about CDMA. And the bottom line is that this rate adaptation can give us a lot of system throughput enhancement compared to a fixed rate system. And again, if any one of you like, I have papers published and that you can refer to, but that may be the area that you guys are very familiar with. And should I go in or?
You want to do it like in 5 minutes? Just tell us briefly what you're doing.
Okay. Just a few slides on some of the key results, okay?
So here you have like several users now? Is that the...
What's that?
So you have more than one user now?
Yeah.
Okay, so you're going to combine multiple axes with some of your ideas here?
Yeah. This is basically what we look. We look at the performance of a network with fixed rate modulation and compare that to the adaptive system that will have variable packet duration, terrestrial star topology, looking at these variable asset schemes, and trying to understand the networking impact of it. Just a few results here. Bear with me for a second. For ALOHA and for CSMA, this is the system's throughput that you will see for a fixed rate system compared to a adaptive rate system. And I skip all the analysis on the system throughput analysis using the variable package duration. And it's a typical throughput versus the off-the-load type of curve that you would use. And we're doing that across different user profile. We have uniform user profile in the shell, or you have linear type of user profile. And we find the same system performance improvement. Basically boils down to the fact that being able to pump the data through the channel as quickly as you can not only create throughput improvement to yourself, but much more importantly, will reduce the chance of collision or other bad factors that will do to the other users. And in turn, it will even boost up the system performance even more. That's the bottom line. And same trend for CSMA as well as ALOHA. When it gets to CDMA system, the total arena change, because what becomes dominant now is the multiple access interference. And what we come up with the rate adaptation now is not trying to steer the processing gain to match the channel condition, but more importantly, we propose to adapt the processing gain uniformly to the outflow in the channel, which is the number of active users or effective number of users if you're counting the intercell interference.
What kind of assumptions do you make about received powers of users?
We compare our system to ideal power control CDMA system. Our system basically uses, say, a fixed. There are three different scenarios that we look at. One of them is that we use fixed transmission power for all users and vary the number of processing in depending on where the mobile is located. Secondly, we use rate control in conjunction of power control and trying to understand that. So essentially, we are steering the rate adaptive OFDM system in a CDMA arena and trying to study the impact of rate control versus power control to come up with the best system that we can propose. And that answers some of the networking issues, throughput delays versus the fixed rate counterpart. And that basically ends my talk. We're looking at different areas in frequency, in physical layer, looking at network link layer approach. And bottom line is that we try to control the processing of this system to either the channel condition or to either the overflow of the channel, depending on what kind of access schemes you use. And that's basically it. And I skip a lot of details, and I have a list of publications, about 12 of them. If you like, you can dig further, and there's reference on that too.
Any other questions?
What's the model assumption on your CDMA? Like, do you use random codes? Do you use simple distribution?
We use typical random code assumption for the user, so the Gaussian assumption for MAI and all those is applied. Yeah. This is a slotted CDMA system that we assume. Yeah. And I don't have to say more about, in terms of talking about the CDMA, a lot of you are very familiar. If you have interest, you can talk to me after that. I can point you to the paper and all those. And any questions?
All right, let's thank John.